First is to take 6 aerial images at an altitude of 60 meters, drop simulated supplies of 50 grams at designated target, and of course be cost effective.
Now for the flight control, basically you can see over here, this is our mock-up of our craft. As you can see, for the flight control, basically all we have to do is vary the RPM. So to increase, to pitch forward, so to speak, all you have to do is drop the RPM of the front two motors, increasing the RPM of the back two motors, and the aircraft will pitch forward. Now the same concept applies to rolling left and rolling right. Now because you can see that our craft is symmetry. So all you have to do to yaw is to rotate the clockwise rotation motors faster than the anti-clockwise, and that will cause a pop effect, causing the aircraft to yaw. Now without further ado, I now unveil to you Carbon, our quad rotor design.
Okay, and moving on to the quad rotor design, and we'll touch on all the components on our quad rotor. So firstly, the frame, we're using a carbon fiber Terra Ironman 650 size frame. As you can see, it's lightweight and foldable design helps in transportation. For the controller, we're using the Autopilot Mega 2.5, which is open source and Arduino based. We find this very convenient for us to perform our tuning. And as for the Autopilot Mega 2.5, because it has numerous ports and outputs, you can easily configure it for multi-row missions. For the controller, we have made extensive tuning to various system parameters such as PID parameters, GPS parameters, and certain flying characteristics. For the speed controller, we're using a 40 amps rating ESC, and this is more than sufficient to support the load of our motors. Moving on to the propellers, we're using the APC size 9" by 4.5". Its small blade twist is ideal for a multi-rotor system, as we found out that it has the highest power efficiency for our current configuration. As for the motors, we're using the Tiger 980 kV motors. As you can see, these are high RPM motors. We chose these for the high speed and high stability performance. However, there's a small trade-off, which is a reduced endurance time. For the GPS, we are using the 3DR GPS module. As you can see, it's located on the top of the plastic container. This has elevated the GPS 10 centimeters away from the electrical components, and this effectively reduces the electromagnetic interference on the GPS. And in addition, the plastic container also provides a form of physical shielding for the critical electrical components. As for the battery, it's mounted at the bottom on an acrylic base plate. We're using a 4-cell 4500 mAh capacity battery, which is sufficient to complete the mission. And for the payload. Basically for the payload, we simplify it. It's a simple and cost-effective system. It's a hook and release system. So all you can see over here is there's a hook over here. So it's triggered by this 9 gram servo. So all you have to do is move the arm, and payload will drop. And comparing this design to other design, the payload size or the ration size is not restricted by any container. As long as the craft can carry the payload, it's able to pick up any size payload there is. For the visual system, we're using a Sony 720 pixel CCD camera, and as you can see, it's mounted on acrylic plate, which is cost efficient and light. For the different frequencies, for the video link, we're using a 5.8 GHz FPV system, and the power rating is 200 milliwatts and provides a range of more than 1 km. And looking at the combination requirements, this is sufficient. Now, in default, it comes with a wave antenna, which my friend is holding over there. We will have replaced this whip antenna by a cloverleaf antenna, as this provides an omnidirectional radiation pattern for transmission. As for the data link, the uplink and downlink, we're using the 433 MHz antenna, However, because this is a plain antenna, it requires a direct line of sight to maintain the integrity of the signal. Therefore, manual panning of the ground station, the antenna, may be required. And now, the mission strategy.
For the mission strategy right here that we have, before we go into that, let's talk about some very important aspect which we all know, safety. We have implemented 4 safety nets. The first one being the GPS fail-safe. In the event I lose my GPS signal, my quad rotor here will automatically land at its last known location. And in the event where you have a transmitter fails, you are out of range or you lose some kind of communication there, what would happen if the motors would just cut off and the craft would just come down to the ground. Now that is better than losing the craft and going off into the no-fly zones or injuring someone in the process of trying to try to bring it back. We also have a pilot override system. This is a system where we use a trainer cable between 2 transmitter controls. So if something happens to one pilot, the second pilot can come in and take control of the craft. And the final system here is the redundancy system, whereby if let's say, for example, there's a lapse in the mission plan that we have set out, the pilot can actually override the thing and manually control the aircraft and bring it back down. Okay, so for the mission strategy down here, this is from what we understand we have to actually do in orbit and for the qualifying round, and we have actually set our waypoints in this manner as we define this as an orbit to us. For the actual flying, based on the challenge booklet that was given to us down here, we've plotted the waypoints on our system and calculated each individual distance from the respective waypoints, and as well as the mission requirement at each stage. So for example, from home at the top down here, I will take off to 60 meters and it will take me about 2 meters, take me for 46 meters to waypoint 2. And that will go on there. So the total distance here is 1.3 kilometers, and we have an estimated flight time of 5 minutes for this course. Okay, so basically in a multi-rotor simulation mission down here, when we compare a multi-rotor and a fixed wing, we have maneuverability and control. We are able to hover, which is something a fixed wing can't do. There's an agile transition of flight, and VTOL being a very important perspective in case you don't have a runway. This, however, is still something in development. Something that can be worked on in future would be the speed and the endurance of such a system, and probably to do unique missions in the indoor navigation down here.
So to end off with our presentation, we have a short teaser of what we're going to be doing tomorrow. So please enjoy.
นี่ที่ออฟฟิศผมนี่รีพรีเซนต์ที่ออฟฟิศเอาไปตอนเทสไฟก่อนมา
So this is the end of our presentation. Thank you very much for the kind attention. Any questions?
Yes, any questions, please? I can feel now, I can tell you, everyone, I can tell that this is becoming a very tough competition. I thought the first three was very good, but this one even good, better as well. So this is a hard job for our judge to decide.
Thank you.
Is there any questions? The last one. Then, if there is no question, please give a big hand to